Hi, good morning, good afternoon, good evening. I hope you are having a great time at this conference. My name is Sourabh Agarwal and I lead program management for Azure SQL Edge. And I am excited at the opportunity to spend the next hour or so talking about Azure SQL Edge and the capabilities the product offers. In this session today, I am joined by my colleague Siya Krishnan. Siya, over to you.
Hi everyone. Thank you so much for joining me today. I hope you're having a great time at the conference. I'm Vasiya Krishnan, or Sia, and I work as a program manager for the Azure SQL Edge team in Microsoft.
Thank you, Siya. So what we'll do over the next 60 minutes or so is talk about the product overview. We will look at some of the capabilities and features offered by the product. And then we will look at some of the demos of how to use these features and capabilities. Post which I'll hand it over to Sia to talk about the customer scenarios and how our customers are using Azure SQL Edge. Finally, we'll cap off this session with a quick summary of the capabilities of the product and the next steps. So before we talk about Azure SQL Edge and take a look at some of the capabilities being offered by the product, let's spend some time talking about the IoT landscape and how IoT is helping transform the industries as we know it today. If you look at any of the major industry verticals, whether it's manufacturing, healthcare, automotive, financial, or even in the consumer space around smart buildings and home security, IoT has a presence in almost every single industry vertical. And it's not just that IoT has a presence. IoT is helping these industries transform and meet the requirements of their customers. For example, if you look at the manufacturing industry, the usage of IoT or industrial IoT, as you would hear some people say, is helping manufacturers reduce cost. It's helping them reduce security hazards. It's helping them optimize and their distribution and supply chains. It's also helping them meet the current demands of their customers and also improve their interactions with their customers. Similarly, in the healthcare space, IoT is helping healthcare providers connect their patients in remote and rural areas with doctors from around the world. IoT is also helping in the inventions or the propagation of mobile healthcare devices, which are making gathering of health statistics quite easy for people who cannot make that trip to the nearest pharmacy or to the nearest provider. Similarly, in the commercial space, IoT is helping us optimize our homes to be more secure and to be more efficient when it comes to energy usage and other factors. The usage of IoT in the various industry segments has grown tremendously over the last 5-6 years, and it's expected to grow at a very fast pace in the next 5 years. Gartner predicts that almost 80 billion connected devices would be available by the end of 2025, and these 80 billion devices would be generating data to the tune of 180 gigabytes in the next 5 to 10 years. Now, this growth in data and the number of IoT devices poses its own challenges. We'll talk about the challenges in a bit, but let's try and understand what is helping this growth in the IoT segment. The first thing is the availability of cheaper hardware. We have more compute power available in smaller chips now than it was available 10 years ago. And that computing power has become cheaper steadily over the last 10-12 years. Similarly, there is innovation in the space of 5G, innovation in the space of mesh technologies, which is helping these IoT deployments become more prevalent. Now, talking about the challenges itself, The challenges associated with the IoT sector can be categorized into two broader buckets. One is related to the network and infrastructure. The second is with respect to the data itself. Let's talk about network and infrastructure first. By network and infrastructure, I mean primarily the network connectivity and the infrastructure needed to establish network connectivity. There are still regions in this world or on the planet where network connectivity is not yet available. And if it's available, the bandwidth is either too low or the cost is too prohibitive to be able to send high volume of data through that network. 5G promises to solve some of these problems, but availability and cost would still be a factor. Then the second aspect is with respect to the data. Given the growth in the IoT devices and the growth in the volume of data generated from these IoT devices, it's impractical to take all of that raw data and send it to a cloud or a data center target. Essentially, what needs to happen is you take this data and you process this data at the origin itself before that data can be moved to a cloud target or a data center target. Now, the second important thing is in terms of security. As more and more devices gets added to your infrastructure, that many more number of endpoints are exposed. And it becomes really important for organizations to be able to secure each and every endpoint and the data originating from these endpoints so that it does not get in the hands of some rogue user or some rogue element. The third thing is with respect to real-time analysis. There are applications of IoT, especially in the context of a connected vehicle or an autonomous vehicle, or in the context of an oil rig, or in the context of the energy sector, where real-time analysis of this data is very important. And it is not practical to wait for the data to be shipped to a cloud or a data center target for it to be processed first, and then you take the actions on the edge or on the IoT side of the world. The last but not the least is the scale and perf aspects of your data needs. Given the volume of data originating from these IoT devices and the fact that you need to process this data at the point of origin itself, scale and performance becomes very important. And as such, you need to invest in technologies or products which provide you that scale and performance to meet your IoT requirements. This is where Azure SQL Edge comes into play. Azure SQL Edge has been designed keeping in mind the challenges which IoT industry or the IoT segment faces today. The features in Azure SQL Edge are built and optimized to help you solve some of these IoT scenarios. Azure SQL Edge is built using the same SQL engine which powers Microsoft SQL Server and Azure SQL. And it is designed to run on these smaller edge servers, edge gateways, and IoT devices. When I say IoT devices, it does not mean very small, low computing power devices, but essentially devices in the range of 2 cores, a few gigs of memory, where you can run a database platform. Azure SQL Edge can run not only on Intel and AMD processors or devices, but it can also run on ARM Pro64 processors. One of the biggest benefits of Azure SQL Edge, and given the fact that it's built on the same SQL engine as Microsoft SQL Server and Azure SQL, is the perf security management capabilities which are offered by the platform across the spectrum of devices. So you take the application, or whether you are running in Azure or you're running on premises with Microsoft SQL Server, or now you're running Azure SQL on the edge, you get a similar surface area in terms of both programming, management, performance, and security capabilities. which makes it very easy for you to extend your current skill sets and your current applications to the edge. Azure SQL Edge is designed to be deployed in either a connected scenario, and we'll talk more about the connected scenario in a bit, in a semi-connected scenario, or in a totally disconnected air-gapped scenario. We'll talk about the disconnected scenarios also in a bit. The primary objective here is, no matter the deployment aspect or the nature of the deployment, Azure SQL Edge should offer the exact same capabilities and performance and scale. So what do we mean by the connected scenario? In the connected scenario, or the way we define a connected scenario, is when Azure SQL Edge is deployed through IoT Edge and IoT Hub as an IoT Edge module. The disconnected scenario is when SQL Edge is deployed as a standalone container on top of a Docker host or on a Kubernetes platform. The objectives are to provide the same capabilities and experience across the two different deployment platforms or deployment scenarios. So let's take a closer look at some of the capabilities which are offered by the product. Azure SQL Edge uses a fully containerized deployment mechanism, in the sense that it is only available as containers, and that are Linux containers today. These containers can run on Intel platforms or AMD platform or an ARM64 platform, giving you the range of, or the choice of devices to run SQL Edge on and create your IoT solution. Second, SQL Edge offers native data movement capabilities to Azure. The objective is that you have all of this data on your IoT devices or on your edge computing devices. And once you have processed that data, you want that data to be stored for long-term retention and scale analytics. That's where the data movement capabilities of Azure SQL Edge come into play. We offer capabilities through both the streaming layer and through the batch processing layer to move data as a continuous stream or as a batch to Azure targets. And this data movement is bidirectional, in the sense that you can move data from SQL Edge to one of the cloud targets in Azure, be it Cosmos DB, be it Blob Storage, be it Synapse, be it Azure SQL, or any other data services in Azure, and also at the same time bring data down from Azure to your edge devices. Think about a scenario where you have some reference data sitting in one of your cloud databases, and you want to bring that data down to your edge devices for processing, right? That's where the data movement capabilities come into play. The third thing we are bringing to Azure SQL Edge is the same performance and security characteristics of Azure SQL and Microsoft SQL Server. We have taken all the security features from Microsoft SQL Server, and we have incorporated those into Azure SQL Edge. So things like transparent data encryption, always encrypted, your row-level security, data masking, all of those characteristics or capabilities are present in Azure SQL Edge. Similarly, in terms of performance, we have taken performance aspects of Microsoft SQL Server or Azure SQL, which makes sense for an IoT Edge sort of deployment, and we have brought it to Azure SQL Edge. So for example, we have things like fast recovery, accelerated database recovery, your column store indexing, compression, all of those enabled by default in Azure SQL Edge. Azure SQL Edge also introduces new capabilities around data streaming and time series. Data streaming capabilities in Azure SQL Edge are powered by the same engine which is used for Azure Stream Analytics and provides similar capabilities as Azure Stream Analytics. We are constantly working on improving or adding the number of source and target pairs which can be used for streaming data to SQL Edge and from SQL Edge. Today we support streaming from IoT hubs, IoT Edge Hub, and Kafka. And in the future we have plans to add more streaming source target pairs. The time series capabilities in Azure SQL Edge is twofold. One, the capabilities offered by the streaming layer, where we provide native capabilities around tumbling windowed aggregation, anomaly detection, windowed analysis of data and stuff like that. And then there is capabilities which are being added to the SQL engine around time series specific functions and time series specific storage optimizations. We'll look at some of the time series specific optimizations or capabilities which we are adding in a bit. Azure SQL Edge also offers built-in ML inferencing capabilities, in the sense that Azure SQL Edge ships with its own implementation of the ONNX runtime, that is the Open Neural Network Exchange runtime, which provides you the ability to train and test your models in a language or toolkit of your choice. And as long as the models can be converted into an ONNX framework compatible model, those models can be deployed to Azure SQL Edge for inferencing on the edge. The scenario which we are trying to solve for is you train and test your model in the cloud or in your data center, and then once the model has been trained and you have enough confidence on the quality or the accuracy of the model, that model can be deployed to your Azure SQL Edge and run inferencing on all the IoT data which you are capturing with Azure SQL Edge. We are also working on providing capabilities which would allow you to do model management within Azure SQL Edge. So essentially, provide you capabilities which will allow you to take models from a repository or a registry, understand if that model is better or worse than the one currently deployed to your Azure SQL Edge, and take a choice or take a call on whether you want to deploy that new model or not. So some of those things are in plans and would be available in the future versions of Azure SQL Edge. With that, let's look at some of the capabilities of Azure SQL Edge and how they can be used to create an IoT solution. In the first demo, we'll look at data streaming, specifically streaming from a Kafka server. In this case, we have machine telemetry data being piped to a Kafka server, and then from there being read into SQL Edge using the streaming capabilities of SQL. And then once that data has been read in SQL, we perform anomaly detection and ML inferencing on that data. So let me go ahead and switch my screen from the PowerPoint to the demo environment. So here I have a connection to my IoT machine or IoT device where all my demo modules are running. So the first thing we have running on the device is a Kafka machine telemetry module, which basically emits machine telemetry data to the Kafka server. Let me go ahead and run a quick Docker logs output on the machine telemetry data to show you the output which is being generated by the machine, or the telemetry data which is being generated. So we have this data coming in every few seconds, and there are about 10 different values which are being generated as part of this demo environment. So we have machine pressure, machine rotation, the vibration, and the machine ID, the timestamp, all of those data being emitted by the app or the module, and that data is being sent to a Kafka server. Now, this data, once it reaches the Kafka server, from there it is being read by the SQL module using the streaming layer. And what you see over here is the statistics of the streaming module. I'll talk more about what this statistics, and where are these statistics coming in from. But for the purpose of the discussion, let's stick to the fact that these are the statistics, the streaming statistics from the Kafka server. What you do see over here is the number of input events which were read from the Kafka server, the number of output events which are basically written to SQL, and I'll talk about why there is a difference between the number of events being read and the number of events being outputted to the SQL table. Right? And then you have other matrices around if there were any errors, what is the size of the inputs, what was the size of the output, so on and so forth. Right? Now, where is this statistics coming from? So let's switch back to my SQL Server Management Studio. So what I've done for the purpose of this demo is I've created a streaming job within SQL where the streaming job is called telemetry data. Now this streaming job is running two different stream queries. The first stream query is this one with the with statement. So essentially what it is doing is it's creating a sort of a pseudo table or a pseudo CTE table on the inputs from the Kafka server, and then it does anomaly detection on that data. And we are using two built-in anomaly detection functions. One is the spike and dip, and the other one is called the change point, to determine if there are any anomalies in the data being captured. For the purpose of this demo, I have kept the accuracy rate to 95, which is basically you look at there should be a 95% accuracy in the anomalies detected. And I've also set the limit duration to about 30 milliseconds, which essentially means that it will look at the last 30 seconds of data to figure out if there is an anomaly or not. Right? And then once I have identified the anomaly or if or not there is an anomaly, that data is being written to a SQL table. In this case, it's being written to my SQL table called machine anomalies. The second query as part of my streaming job is a raw data dump of this telemetry output into the machine input table. Sorry, the machine inputs into the telemetry output table, and this telemetry output table corresponds to the telemetry table in the database. Right, so that's my streaming job. It's taking the data from my Kafka server. We are doing windowed aggregation on this data. So in this case, I am aggregating the last 10 seconds of data using the tumbling window function. And then I'm also doing anomaly detection on that data while the data is being read in. And then at the same time, I'm also dumping the raw data for future references. Right, so if you look at let's go and look at the output from these tables. So for my telemetry table, I can go ahead and dump the last 10 records to see what were the data captured. So you would see that there is the voltage, the rotation, the pressure, the vibration, and if there were any error matrices captured as part of the machine telemetry. And then I can run a similar query on my machine anomalies data to figure out if there were any anomalies. And as you can see, for all the machines in the last 10 seconds or so, we have identified some anomaly in the pressure data. Whereas on the vibration data, there is no anomaly. Right? So in this demo, we saw how you can use the streaming capabilities of Azure SQL Edge to read data from a Kafka server and then also perform windowed aggregation, anomaly detection, and at the same time also dump raw data into a table in SQL. In the second demo, we will look at retention policy-based data cleanup. Now, collection and storage of data from connected IoT devices is important to derive and gain operational and business insights from this data. However, given the volume of data originating from these devices, it becomes important for organizations and enterprises to carefully plan the amount of data they want to retain and at what granularity. Right? While retaining all of this data is desirable, it's not always practical. Right? So to address some of those scenarios in Azure SQL Edge CTP 2.3, we introduced a new feature called data retention policy. And once the data retention policy has been defined on a database or a table, there is a background task which runs to clean up old obsolete data from these tables. Let's take a look at this feature in action. So setting data retention on a database or a table is fairly easy. It's as simple as a single alter database or an alter table command. So in the example over here, let's go ahead and create a database which we will use for data retention tests. So let me go ahead and do that. And then once the database has been created, or if there is an existing database, you can set data retention on that database using the alter database set data retention on or off command. Now, to check if the database has been enabled for data retention or not, you can run a query on sys databases and there is a column we have added, is data retention enabled, which would be set to either 0 or 1 depending on whether data retention has been set on the table or not. So in this case, we can see that data retention has been set on the database data retention test. So let's go ahead and create some tables in this database. So the first table I'm creating is a table with a primary key clustered index. And if you notice the new syntax, we are enabling data retention on this table with the command data deletion equals to on. And then we are also specifying a filter column based on which SQL will determine if the rows are obsolete or not. And then the last parameter we are defining is called the retention period, which essentially defines at what period the rows become obsolete. So let me go ahead and run that. And then similarly, I'm creating another table which is unique non-clustered index with the same syntax. The data retention or data deletion equals to on, filter column equals to a date time column, and retention period in this case is 1 week. And the third thing I'm doing is I'm creating a table with a clustered column store index and defining a retention period of 1 week on the table. Now, if you run a query against sys.tables, you would see that the output of there are few columns added to sys.tables which define the retention period, the retention units, and the unit description for data retention. And if you want to run a query on sys.columns, there is a new column added to sys.columns which tells you whether or not a column is being used as the filter column for data deletion or not. Right, so let's go ahead and insert some data into this table. So the first thing I'll do is I'll go ahead and insert 5 records into my data retention table 1, which was my primary key clustered index table. Now, and let me go ahead and run checkpoint. In SQL Edge, the default recovery level is, or the recovery model is simple. So I want to get rid of my log records for the time being. Now let's go ahead and look at my log and see if there are any records. So there you see only 3 records, which is what was written by the checkpoint operation. Now let's go ahead and call the manual cleanup operation on this task. In our case, we had set the retention period to 1 day, so automatic data cleanup won't run, but we can always go ahead and run the manual cleanup operation on that table. So in this case, I'm specifying the table on which the manual cleanup should run, and this is an optional parameter which outputs the number of rows deleted. And we can go and check that there were 5 rows and you have 5 new log records indicating that 5 rows were deleted from the table. Now let's do the same thing on a column store index table. So let me go ahead and insert 5 rows into this table and alter the index. That is basically rebuild the index. Now what this will do is it will close the row group with the 5 rows in it and compress the row group. We can go and check this using the sys.column store row groups catalog view, and you can see that my table has 1 row group which is in the compressed state. Let's add 5 new records into the tables for a total of 10 records in the table now. So if you notice the output of sys.column store row groups now, you have 2 row groups in the table. One is in the open state, the other one is in the compressed state, and both have 5 rows in it. let's go ahead and make sure that there is no checkpoint and all that. Now let's go ahead and run the manual cleanup task on this table. So you would notice that there are 10 rows which were cleaned up by the manual cleanup task, which essentially means that rows in both the compressed row group and the open row group were deleted by the manual cleanup task. Now these are obviously rows which were outside of the retention period, because if you notice my query, I had inserted rows which are at least 10 days older, right? So now let's go ahead and run a query on my row groups, and you would notice that both the row groups, the data has been deleted. In the compressed row group case, the rows have been marked for deletion using the delete bitmap. If I rerun my alter index rebuild operation, this would clear all the deleted and ghost records from the table and results in a column store index with 0 row groups. And if you have to disable data retention on a table or a database, you can run the alter table command to set data deletion equals to off. Similarly, you can set data deletion or data retention equals to off for a database. So in this demo, we saw how easy it is to set data retention policies on your databases and tables and use those policies to automatically purge obsolete data from the database. Today, the implementation uses delete queries and column store optimizations. We are still working on improving the delete query performance and how we optimize the performance of this purging on HOBT indexes. In the next demo, we will look at how machine learning based inferencing happens in SQL Edge. For the purpose of this demo, we will train a MLP classifier, basically the multi-layer perceptron classifier, using the sklearn neural network package in Python, and then deploy that model to SQL Edge to run inferencing. For the purpose of this demo, I'll be using the ECG classification data to train my model and run inferencing on my model. So what I have here is Azure Data Studio with a Python notebook running in Azure Data Studio. And for the purpose of this model training, let's import some Python packages which are needed for the purpose of the training. So in this case, I am importing Python packages like the pandas, the pyodbc, the sklearn packages which we will use for the training, and then the rest of the packages around Onyx and Onyx runtime. And then let's also pull in some data for our model training. This data is coming in from my Azure SQL Database Edge instance. And this is the ECG classification training data from MIT. So this takes about 30 odd seconds to read all the data from the database. This is approximately around 100,000 odd records with different classification data. And then once the data has been imported into the data frame, we will run a basic redistribution or resampling of the data so that I have equal samples for all the different types of classification we will work on. Once that classification has been done, I'll distribute my table or the data frame into training data set and testing data set. And in the next step, we are creating a model pipeline where the first step of the pipeline is to do a column transformation, and the next step of the pipeline is to run the MLP classifier, which is basically the multi-layer perceptron classifier. This is one of the neural network classifier functions available in the sklearn package. So let me go ahead and do that. This takes about 30 odd seconds also, primarily because I have reduced the number of max iterations. You can go to a higher number, but that would in turn take longer time for the model to be evaluated and to be available for rest of the steps. So let's give it a couple of seconds or a few seconds to let the model train and run through the iterations. Then once the model has been trained, we run 2 quick steps to check the score and the accuracy of the model. In this case, I am using the model.score parameter to identify what was the score of the model. And in the second case, I am using my training dataset or the output from the training dataset along with the actual output from the training dataset to understand what was the R2 score between the predicted output and the actual output. So you notice that my model has been trained. Let's go ahead and look at the score of the model. So the score of the model indicates about 0.89, which is fairly okay. If I were to increase the iterations a bit more, I might get a higher accuracy of the model. Let's go ahead and run this query also. You would notice that the R2 score is around 0.77, which is fairly okay, and the mean root square error is about 0.45, which is also decent. The next step of the model is where we will convert the model into a Onyx compatible model and save that model. So I'm saving that model as a ECG model sklearn on my disk, which I can use later to go through the characteristics of the model. Now, for the purpose of this demo, we are going to write this model into the models table of my SQL database. So let me go ahead and do that. This will write the model as a var binary input or a var binary field into the models table. Now, once the model has been written into my SQL table, I can go back to my SQL table and run machine learning based inferencing on the data. So for the purpose of this data, I have a generated data set from my ECG module, and I'm going to run inferencing on that. And in this case, I'm going to get the last 10 rows of the data and run inferencing on that. So let me go ahead and run that. So my inferencing ran on that data, and for majority of the data set, it identified the ECG classification of 1, and then for a few data points, it classified it as a normal ECG reading. So in this demo, we saw how you can train a model or a machine learning model in Python using one of the Python packages and then deploy that model to Azure SQL Edge. The machine learning services in Azure SQL Edge make it really simple for you to train and test your models in the cloud or in the data center, and then bring those models to the edge for local inferencing. Now, I'll pass it over to Sia to talk about our customer scenarios and how these customers are using SQL Edge to transform their businesses. Over to you, Sia.
Customers have been transforming their businesses by using Azure SQL Edge. It has played a key role in improving factory efficiency, cost savings, improving processes, enhancing employee productivity, and accelerating delivery time. In short, Azure SQL Edge is enabling customers to move to Industry 4.0. Fugro. Fugro is a geointelligence provider that helps clients in the energy sector gain vital insights for planned marine projects. So these marine projects include offshore wind farms, etc. To support its clients in early project phases, Fugro sends a team of oceanographers, meteorologists, and hydrographers to collect environmental data such as water depth, wind waves, currents, and temperature. This marine geodata, which can be collected through sensors on Fugro vessels or ocean buoys, is vital to understanding how a structure such as a wind farm might behave in extreme climates. The offshore locations where Fugro collects data are often remote, and acquiring this data quickly and consistently was challenging. Additionally, the quantity of data collected meant that analytics could be performed only on land, leaving Fugro unable to drive real-time insights. The company set out to fix these problems by moving analytics to the cloud and network edge. The Fugro team migrated its on-premise SQL Server environments to Microsoft Azure SQL database in the cloud. Then, Azure IoT Edge and Azure SQL Edge were deployed locally at the offshore project site on unmanned vessels. Thanks to Azure SQL Edge, time series data was now able to be ingested, queried, stored, and processed locally at the edge, saving the company significant time and costs associated with latency and bandwidth usage. The solution is so efficient that Fugro has reduced the time needed to process and deliver monthly data reports from offshore locations to client dashboards from 2 weeks to 8 minutes. With the help of IoT Edge and Azure SQL Edge, Fugro has improved the management and efficiency and resiliency of its solution infrastructure. Next, we have Achilles. Achilles is a leading plastic film manufacturer, and they were looking to improve their efficiency of the factory processes, that is around improving data analysis and standardizing employee production. Precision was something that was key to Achilles. They envisioned a system that gave crews access to the latest procedures for every production run. Using Azure SQL Edge, their IT team developed the Achilles shop floor data collection system, which provides crews with both an easily updated digital handbook for setting up every job and an on-site data collection mechanism. The company loads the digital handbooks on its Microsoft SQL server, and the data is transmitted to handheld devices on the shop floor for up-to-the-minute guidance for every job. The crew uses Surface devices deployed on the shop floor that run the shop floor data collection system and Azure SQL Edge. So the devices display the digital handbooks for each job for easy reference, and crews update them periodically to document machine settings, which then syncs to the back on the company's on-premise SQL service. This production data, which once languished in a file cabinet, is now providing value. Along with providing guidance for the crews running the shop floor equipment, they're collecting values about shop floor conditions and machine settings that enhance quality. All of that feeds back into production design and manufacturing processes standards to give them control they have never had before. Next up is Raven. Life-saving hospital assets like ventilators and infusion pumps need to be mobile, but that mobility also means that devices can be difficult to find and then monitor them when you need it. This is a problem that has only been compounded by the COVID-19 pandemic, when the difference between good and poor asset tracking and management of particular assets in the hospital has truly become a matter of life and death. End-to-end data management and analysis to take the right decision was critical to Raven's customer. There are always challenges around ensuring data security at all points on the location. Some of the key outcomes were creating an automated reporting dashboard. These custom reports and dashboards automatically populated and are distributed to the relevant medical professionals and teams. These dashboards also led to better visibility of vital assets using real-time location to have full control of where and how ventilators are being used. This in turn led to better resource utilization. Further, there was always a scheduled asset maintenance that happens regularly, which can mean taking assets offline unnecessarily. Kind of leads to a shrunken pool of resources when you need them the most. Predicting when action is required means you can avoid unnecessary downtime. All of this, in the end, resulted in saving more lives. The IoT solution was designed primarily to obtain real-time visibility of ventilator location and utilization. The process began by identifying the critical data that needs to be collected to deliver the necessary goals. This included ventilator status and location and the medical bed status and location, and finally the schedule information. Azure SQL Edge was deployed as a part of Azure IoT PaaS platform on Raven certified Aero devices. As you can see here, some of the key features of Azure SQL Edge, that is built-in data streaming, time series capabilities, especially around anomaly detection and data aggregation, played a crucial role in real-time analysis of the ventilator information. Further, this data is also sent to the cloud, which powers Raven's dashboard and also aids in training of ML models that are deployed to the edge for ML inferencing. As Raven and Arrow say, investing in edge data services and platforms such as Azure SQL Edge creates the foundation for them to accelerate the delivery of new products and services to their clients. In this demo, we will see how Raven and Microsoft are working together to make healthcare IoT solutions more intelligent. For the purpose of this demo, I'll be assuming the role of a maintenance supervisor in the hospital. One of my key responsibilities is keeping our ventilators operational, a time-consuming and critical task in the age of COVID-19. What I have in front of me is Raven's customized dashboard. You can see the map of my hospital with the location of multiple ventilators across the buildings. If you look at the data closely, you will realize that it is often time series in nature. I'm tracking multiple data points for each of these ventilators, such as which room are they located in, what is the temperature of the device in there, battery state of the ventilator, and also battery of the RFID tracker on the ventilator. This was made possible by Azure SQL Edge that has been deployed on these devices. Native data streaming capabilities on Azure SQL Edge enables the devices deployed on the hospital floor to capture the real-time information from the ventilators. This helps me make most of my assets without having to spend my whole day conducting in-person checks. In addition to giving me visibility into imminent failures by collecting data over time and combining it with information like service records, I can start to build a proactive maintenance plan to minimize downtime and maximize quality of care. The data that I have been collecting at the edge is aggregated and sent to the cloud storage. In this case, it's an Azure SQL DB. This is possible because of the native data movement features supported in Azure SQL Edge. And by sharing the same data with my medical colleagues, they can remotely review and validate the device configuration irrespective of where they are located and take timely actions as needed for the patient's well-being. Let us now see how SQL Edge makes all of this possible. SQL Edge uses the same SQL engine as its data center-based counterparts, and as a result, I can use the tools I'm already familiar with, like SQL Server Management Studio, or in this case, Azure Data Studio. From Azure Data Studio, I can deploy SQL Edge directly to an existing container environment or an Azure IoT Edge device. Here, you can see the list of deployment targets available for deploying your Azure SQL Edge instance. As I mentioned, it could be a local container instance or a remote container instance, and at the same time, you can also deploy it as a part of your Azure IoT Hub, either a new one or an existing one, or on multiple devices on an Azure IoT Hub. In this case, I have already got my SQL Edge environment deployed, so let me connect to it. Just like any other SQL server, I can use a full range of T-SQL query syntax and get full intelligence support in this editor. From this query, you can see the raw data coming from the ventilator sensors across my hospital. The data frequency and volume means relaying this to the cloud for analysis isn't a good choice. Let's see how SQL Edge can make sense of the data locally. First, if you look closely, you'll notice some null values in the results of my last query. This can happen when the sensors fail to provide timely responses or unexpected values. Missing values makes time series analysis much more difficult. When dealing with time series data, it's often possible that this missing values for attributes occurs because of the nature of the data or because of interruptions in data collection, and that results in time gaps in the data set. So in Azure SQL Edge, a new syntax was added to T-SQL, that is the last value and the first value functions, which provide mechanisms to impute missing values based on the preceding or following values in the dataset respectively. The new syntax also adds ignore nulls or respect nulls clause to the last value and first value functions. So let's go ahead and run this query to see what happens by using the last value function. We're going to look at it as a form of a chart. So by using the last value function, what we see here is we have replaced the missing values with the most recent sensor reading, and this is just one of a number of time series capabilities in SQL Edge for local analytics. The next thing that we are going to see is around data retention. Collection and storage of data from connected IoT devices is important to drive and gain operational and business insights. However, given the volume of data originating from these devices, it becomes important for organizations to carefully plan the amount of data they want to retain and at what granularity. While retaining all the data at all granularity is desirable, it's not always practical. Additionally, the volume of data that can be retained is constrained by the amount of storage available on the IoT or edge devices. In Azure SQL Edge database, administrators can define data retention policy on a SQL Edge database and its underlying tables. Once the data retention policy is defined, a background system task will run to purge any obsolete or old data from the user tables. When managing real-time data, our edge device not only needs to be able to handle on-demand queries, but also perform analytics over the incoming stream of data in near real time. For example, here we can see a recent device anomaly where the temperature has increased unexpectedly. The maintenance team then receives a proactive notification of this issue. Azure SQL Edge provides a native implementation of data streaming capabilities called T-SQL Stream. So it provides real-time data streaming, analytics, event processing to analyze and process high volumes of fast streaming data over multiple sources simultaneously. As with stream analytics, T-SQL streaming recognizes patterns and relationships in information extracted from a number of IoT input sources. In this case, these are the ventilator devices that are there on the hospital floor. So you can use patterns to trigger actions and initiate workflows. So T-SQL streaming works in exactly the same manner as Azure Stream Analytics. So a stream analytics job usually consists of a stream input, a stream output, and a stream query. So once that is done, we will be creating a streaming job in this case with anomaly detection built in, and we are using the anomaly detection spike and dip cast over here. And then post that, we will be starting the streaming job, and at the end, the result that we are going to see is what are the anomalies with respect to the temperature of the ventilator that is coming up on ventilator number 3. Let's go ahead and run this query now. So here you can see that we have a score that has been assigned to each of the values that are coming out from the table, and also we have also seen whether it is an anomaly or not. Given that we wrote a query that clearly picks out only those records that are above a temperature of 80 degrees, which means it's above, which means that we are considering it as an anomaly, you see that the score is 1 for every time the temperature is above 80 for this particular ventilator. While alerts and other key operational telemetry messages are best routed to the cloud via IoT Hub, bringing aggregated data sets up to the cloud can be more efficiently done through Azure SQL Data Sync. SQL Data Sync is a service built on Azure SQL Database that lets you synchronize the data you select bidirectionally across multiple databases in Azure SQL Database and SQL Server instances. Because SQL Edge is built on the latest version of the MySQL Server database engine, any data synchronization mechanism that's applicable to a SQL Server instance can be used to sync data to or from SQL Edge instance running on an edge device. Setting up synchronization between a database in Azure SQL DB and a SQL Edge instance by using SQL Data Sync involves 3 key steps. First, you use the Azure portal to create a sync group. You can use a single hub database to create multiple sync groups to synchronize data from various SQL Edge instances to one or more databases in Azure SQL DB. For the purpose of this demo, we have already created a sync group called the DB sync group, and then those are what is called the sync members to the sync group. So set up the sync group to select the tables that will be a part of synchronization. So after you complete these steps, you will have a sync group that includes a database in Azure SQL Database and a SQL Edge instance. So when you look closely into the logs that is available over here, you will see that the sync has been happening successfully every couple of minutes with this database that is on the edge. What we'll be doing next is actually querying this cloud-based Azure SQL DB to see if the records have been syncing properly or not. So let's go to the query editor. We'll be logging into the SQL database using SQL Server Authentication. Now we are into it. We'll just be looking at the maximum timestamp that is available on the database to see if the data sync has happened or not. So select max timestamp from real-time census record. Yep. So what we see over here is the maximum timestamp, which is 26th October, and that is the latest sync that has happened to the cloud target over here from the edge table. So with this, it's clear that records from just a few seconds ago are already available for my cloud-based dashboards to visualize and carry out any kind of data analysis or ML training model, as we are going to see next, that is required to be deployed to the edge for inferencing. SQL Edge also has built-in ML capabilities with native support for running ONNX models inside the database. ONNX is Open Neural Network Exchange. And while Edge is the ideal place to run inferencing, mainly to avoid massive real-time data uploads, which is an expensive task, it is not the best place to build models. Once the data is in the cloud, as you can see here, I will be using Azure ML capabilities to train or retrain models that need to be deployed to the edge for better inferencing and anomaly detection. So now let us spend the next few minutes trying to build a model that is going to be used to predict a device failure before it results in a complete service outage. First and foremost, I'm going to import the data set that I have sent to my Azure SQL DB Cloud Target. Once we fetch our data set, I'm going to be using AutoML to evaluate different model types. And as you can see here, I'm running 10 iterations. You can run more than 10 iterations in order to help you choose the best model out there. And what AutoML does is it helps us evaluate different model types, and then it recommends the right one based on what is the best run fitted model that is suited for our data set. So once that is done, thanks to the native support for ONNX, the winning model can now be easily exported to Azure SQL Edge. Now let's see how the model that we have trained here can be used with Azure SQL Edge. So after loading it into the table, we can start referencing it. We can reference it using the native predict statement over here. So let's fetch the latest data for a particular ventilator and then use it to make a prediction on whether it's likely to be nearing a failure. Let me go ahead and run this query. So once that is done, you will see here that for the purpose of this demo, we are looking at 20 different ventilators, and out of which there is one ventilator which has label 1, meaning it is up for service sometime soon. In short, with SQL Edge, Raven was able to provide a more comprehensive asset management solution for their customers through richer historical and predictive analytics across the full real-time data estate only available on the edge. With its SQL Engine foundations, out-of-the-box support for streaming data and AI, and cloud integration through IoT Edge and SQL Data Sync, it is easier than ever to provide a fully featured intelligent data solution on the edge.
Thank you, Sia. It's truly amazing to see how SQL Edge is helping organizations transform their businesses, and in case of Raven IoT, saving lives. Right, so in summary, SQL Edge is the most versatile database platform for IoT and edge computing needs. It not only brings the performance and security of SQL Server and Azure SQL to the edge, it also appends new capabilities around data streaming, time series, AI on the edge, all of that in the same product. Further, SQL Edge offers the same set of T-SQL surface area, which makes it easier for you to integrate your solutions with SQL Server on-premises or Azure SQL running in the cloud. And finally, SQL Edge, since it's built on the same engine as SQL Server and Azure SQL Edge, you can use the same skill sets and tools you use for managing SQL Server on-premises or Azure SQL in the cloud. As a next step, if you're interested in learning more about Azure SQL Edge, please browse to our documentation and our at aka.ms/SQL Edge. And if you're interested in learning about how our customers are adopting SQL Edge and how they are using SQL Edge, the links are available on the page. Finally, before we wind up, a quick shout out to our friends at the Data Platform Summit, the SQL Data Geeks. And if you're interested, there are multiple ways on how you can win prizes. One is if you post a selfie with the hashtag DPS 2020, make sure that you give session and conference feedback and that you visit the sponsors and the exhibitors. That's it from our side. Thank you so much for your time and the patience. Thank you.